Chemistry Comes Alive. What a title. Everybody gets so worried about chemistry. This is not a chemistry class. This is a biology class. So, clear your mind of the negative thoughts that you can't do this or that you'll just fail this part and then you'll just, do better on the rest of it. No thinking like that. I am not a chemist. I'm a biologist. I could not teach a chemistry course. These are very basic concepts that help you understand the things in physiology that we'll discuss later. How things get into the cell, how things get out of the cell, how we have catabolism, anabolism, how things, catabolism break down, how things build up anabolism. So, it's going to be okay. Get your Coke, get your coffee, get your tea, whatever, and let's go play.
At this very moment, there are thousands of chemicals moving through your body, and the reaction of these chemicals are involved in every single physiological process. Since your goal as a healthcare professional is to help your patients maintain a healthy body, it's important to understand the chemistry that enables the body to function. For example, in the emergency room, we treat many patients experiencing dehydration, fluid loss, and electrolyte imbalances. In order to know which IV fluids need to be infused into patients suffering from these disorders, you need to understand the chemical effects that the fluids will have on the patient. When patients are dehydrated, it is important to replace their lost body fluids with solutions such as lactated ringers or normal saline. These solutions are used because of their sodium concentration. Water follows sodium in and out of cells, and getting the right calculation of sodium into the body is critical in rehydrating patients. By having a solid understanding of basic chemistry and biochemistry of the body, you'll be able to help your patients recover from dehydration, fluid loss, and other homeostatic imbalances.
So, I told you in chapter 1 that anatomy is what you see and physiology is how it works. Well, how it works has to do with chemistry. But again, this is not a chemistry class, okay? We have things moving in and out of cells. We have things being absorbed, going from a cell to tissue to blood, then back out. Maybe going to go to the liver. The liver's going to take those little molecules and build it up into a totally different compound to store something. You get the idea. So, basic chemistry. Matter is the stuff that things are made of. Energy moves the stuff. So the term matter is anything that has mass and occupies space, no matter how tiny, right? Now, a lot of times, matter can be seen, or you can smell it, or you can feel it. Not all the time. And mass, the definition of mass is very much the same as weight, except we can weigh something on Earth because we have gravitational pull. And we use the terms, let's say, kilograms or grams or pounds or ounces, things like that. But what you're actually measuring is the mass of something. So the size of something, how dense is something, okay? If you're out and let's say me, I'm going to lie to you and I'm going to tell you I'm 100 pounds. That's a fib. But if I say I'm 100 pounds, that's how we are going to weigh my mass on Earth. Then I get to go out into space in a spacesuit. I am no longer 100 pounds. I'm weightless. You can't weigh me. But am I still the same mass that I was? Yes, I'm still that same quote-unquote 100-pound person. I didn't change. You can't measure it right now. So mass is what you're made of, okay? And let's see, there's different ways it could be. So obviously human beings are solid, but liquid is like water. It has a volume, and you can change shape depending on, are you going to put it in a tall glass? Or are you going to put it in a short glass? Are you going to put it in an oval vase? Or are you going to put it in a square vase? That's a liquid. And then gas is also a changeable shape, and the volume can change because it depends on how much pressure is in that gas. So we can condense, we can shove carbon dioxide into a Coke bottle, or maybe you're a Dr. Pepper lover. So the reason that Dr. Pepper or that Coke is bubbly is because we have shoved gas into that liquid. But that gas doesn't want to be shoved into that liquid, and that's why when you open that lid, it goes psst, because the gas instantly is leaving that area, that little 12-ounce can, and it's left and it's gone out of the can into the air. So he just took up a whole lot more space because you open the can or bottle, whatever. So it decompressed. The carbon dioxide wants to be out. It wants to be free. And when the carbon dioxide all leaves, you have a very flat Coke or Dr. Pepper. You know what I'm talking about. Okay, energy is the capacity to do work. Energy is what moves matter. Okay? It doesn't have mass, it doesn't take up space. But the more work done, the more energy is used up. Energy actually also comes in different forms. But both matter and energy cannot be created or destroyed. So it can get transferred, but it can't get created or destroyed. So you've probably heard the term ashes to ashes, dust to dust. So let's take the spider that you crushed yesterday. He was made up of different molecules, okay? And he baked in the Texas sun, and he's going to break down into tinier and tinier and tinier molecules, and some little bug is going to come along and eat the pieces that are left, and that's going to help him build up whatever he needs to keep going. You get the idea. That matter was not destroyed, it just moved to a different location. Matter is essentially the periodic table in different molecules. So all those elements built up into different molecules.
Energy is the capacity to perform work. Potential energy is energy that is stored. Kinetic energy is the energy of motion. Energy is neither created nor destroyed, but converted from one form to another. This property is called the conservation of energy. The bow and arrow start out with low potential energy. As the archer's arm pulls back the string, kinetic energy from the arm's motion is converted to potential energy in the tense bowstring and arrow. When the bowstring is released, the stored potential energy is converted into the kinetic energy of the moving arrow. When the arrow hits the target, its motion ceases. If energy is neither created nor destroyed, where did the energy of the flying arrow go? Let's rewind and look at kinetic energy in more detail. When energy is converted from potential energy to kinetic energy, some of the energy can be used to do work, but some energy ends up as heat, a type of kinetic energy. Heat is the random motion of atoms and molecules. As the arrow flies through the air, heat is generated by friction between the arrow and air molecules. When the arrow strikes the target, all the energy becomes heat energy. The heat energy is rapidly transferred into the air and spreads out. Heat energy is a very disordered kind of energy. It has the highest amount of entropy, or disorder, of any kind of energy. Where do our muscles get energy to perform work, such as pulling back a bowstring? Our bodies use the chemical energy from food to perform work. Chemical energy is a form of potential energy. When your body breaks down food molecules, the stored potential energy from food can be converted to kinetic energy. The stored chemical energy in food is released in your muscle cells during the process of cellular respiration. Using oxygen, cellular respiration converts chemical energy from food to another form of chemical energy called ATP. Water, H2O, and carbon dioxide, CO2, are byproducts of cellular respiration. The potential energy of ATP can be converted to kinetic energy. Some of the kinetic energy is used to do useful work, such as pulling back a bowstring, but the heat energy that is generated cannot be used to do work.
Okay. Kinetic energy is energy in motion. These are different types of energy. Potential energy is stored energy. So your battery, let's do a AA battery. There's potentially some energy in there, yes? It's stored in there, and that battery is good for quite a while. What makes that battery usable, how you use the energy that is stored, that potential energy inside the battery, is you have to hook up the connections, right? Because you know there's a positive side and a negative side on that battery. You have to hook that battery into a connection to complete a circuit so that those electrons can flow. Otherwise, it's just potential. So the light comes on whenever you complete the circuit, you plug the battery in, and then whatever, the light bulb comes on, or the radio turns on, or, you know, pick something that you stick a battery in. Okay, whatever. Okay, some other forms of energy. Chemical energy. This is the energy that's stored in bonds. So let's say we've got H2O. That's water. There is a bond between the hydrogen and the oxygen. Okay? When you break that bond, you release energy. That energy is going to go be somewhere else. Electrical energy is moving charged particles, like the battery. Mechanical energy is physically moving something. I'm going to move my daughter's desk. That's going to take mechanical energy. And then finally, another kind of energy is radiant energy or electromagnetic energy. So examples would be heat and light. And let's say X-rays. So what's happening is it's traveling in waves. Sound waves. How about that? Energy can be converted from one form to another. So here you go. You have that battery is creating an electrical charge when you plug it into two poles, and then the flashlight comes on. So now you've converted that energy that's traveling around into a little bit of light energy. There's always a little bit, whenever we talk about energy being used, a lot of times a little bit is going to be lost in heat, and I believe that was just mentioned on that previous video there. And in the human body, in biology, in our bodies, energy conversions usually do lose a little bit of heat. Okay, so the periodic table is that guy you saw in high school with all the letters. You know, Na for sodium, O for oxygen, C for carbon, Cl for chloride. Okay, those are the elements. And a single one of those elements is an atom. However, most of the time, they're not very happy being alone. So an atom is going to bond with another atom, maybe even more atoms, whatever, is going to end up making up a molecule. Okay. All right. The most common elements in our body are carbon, oxygen, hydrogen, and nitrogen. You've probably heard organic matter is made of carbon. And for this class, that's a good enough definition right there. Organic matter has a carbon skeleton. Okay. Each of these atoms are going to behave differently, bind with things differently, have a different kind of physical appearance, just like me and you. They're very individual. Okay. What else do I want to say about that? The way that they're made up determines how they bond with other things. That's the other thing I want to say. Okay. When I tell you that here's those different elements, and I already threw out one, Na for sodium. Sodium's atomic symbol is Na, and that has to do with its Latin derivative, natrium. You don't need to know that. But that's what it's called, the atomic symbol. So C for carbon, O for oxygen, H for hydrogen, N for nitrogen. Yay, the four most common things in our body are super easy. Okay, so if I have a single sodium, an atom of sodium, I'm going to tell you it has different parts, and maybe you remember this from high school also. There's a center part called a nucleus, and inside that nucleus you have subatomic particles called protons and neutrons. Protons have a positive charge. They both start with a P. Protons, positive. They get assigned an atomic mass unit of 1. So like it weighs 1. But remember, mass is what it's made of, and you can only weigh something on Earth because we have gravity. So 1 atomic mass unit. Neutrons don't have a charge. They're neutral. So there's that Latin derivative right there. They also weigh 1 atomic mass unit. And electrons are super tiny little things that are zooming around the nucleus, just like in Harry Potter. What was that thing called in Quidditch? The snitch. Zoom, 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 zoom. So tiny that we don't give them an atomic mass unit. They're just tiny. Now, if you take a chemistry class, you're going to learn a little bit more details about that guy. Who cares? We're not in a chemistry class. It is a negative charge, and they're zooming around the nucleus. So would it make sense to have a stable atom? You need the same number of protons as electrons so that it's balanced? Okay. Most of the time, that's what we consider on a periodic table. So on that piece of paper, that's how they're listed out. That's what I just said. Number of positives equals the number of negatives. Protons and neutrons are in the nucleus. Sometimes it's the same number and sometimes it's not. You don't need to memorize those kind of things. We have different kind of models. The one that I just planted in your head was the orbital model. So the one I just planted in your head, I described a central nucleus, and then I described electrons that are zipping around that nucleus like a snitch. Zoom, 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 zoom. So that's what I described. But of course, we can't draw that. So on a piece of paper, it's the planetary model. Like this. So here we go. This right here, we've got 2 red dots come down here, so we have 2 protons. This particular atom also has 2 neutrons right there. If we have 2 protons, 2 positives, then we must also have 2 electrons, 2 negatives, to balance that atom. This is trying to draw the orbital model, not a test question. Okay. So different elements are going to have different numbers of subatomic particles. Okay, they're going to have their own atomic symbol. They're going to have their own atomic number. They're going to have a mass number, a weight, and then they're going to have something called isotopes that we're going to get into. Okay, so the atomic number is the number of protons in the nucleus. If you change the number of protons in an atom, you've just changed the whole element. Hydrogen has 1 proton. 1 proton is a hydrogen. But if it's 2 protons, it's not hydrogen anymore. It just became helium. Okay? The mass number is the total number of atomic mass units inside of an atom. So we're going to say, remember I said that protons have 1 AMU and neutrons have 1 AMU. So, which is atomic mass unit. So, if we had an atom that had 1 proton and 1 neutron, the mass number is 2. Easy, right? Here's examples right here. Remember a minute ago I said just because it has 1 proton doesn't necessarily mean it has a matched up neutron. Here's an example right here. Plain old hydrogen, also called protium, but plain old hydrogen has 1 proton and no neutrons. So sad. He does have to have his balanced out electron right there. So 1 positive, 1 negative. Helium. Helium has 2 protons and 2 electrons. So if he's got 2 P's, 2 positives, he has to have 2 negatives. And you get the idea. 3 protons is going to be lithium. Proton makes the element. 3 protons. Oh, look, this one's got 4 neutrons. Isn't that interesting? Okay, who cares? All right, but if we have 3 protons, then we have 3 electrons. The positives have to match up the negatives. So here's 1, and here's 1, and here's 1. 3. Now, isn't it odd that this dude over here is, oh, dang it, I need my little pointer. Oh, I'm so sorry, I've been forgetting my pointer. 1 proton, 1 electron. 2 protons, 2 neutrons, 2 electrons. 3 protons, 4 neutrons, and then 1, 2, 3 electrons. Okay. So in one of the next slides, I don't know which one, we're going to talk about laying out the electrons in their orbits. The first orbit right here, every orbit is a shell. This is a shell, this is a shell. The first shell can only hold 2 electrons. And for the purposes of this class, I want you to just remember that the next shells hold 8. Every shell wants 8 past the first one. The first one just wants 2. The rest of the shells want 8. Is it more complicated than that? Yes. But for the purposes of this class, past the first shell, all the other guys hold 8. All right. So it's not this slide. That's okay. Repetition is key to learning. Sometimes we're going to have in life an isotope of something. It's the same element. So if I say that hydrogen has an isotope, it's still hydrogen. It's just got something a little different about it. Carbon. Carbon dating is using an isotope of carbon. So what's an isotope? An isotope is the same element, but however it's written on the periodic table, so let's say carbon. Carbon has 6 protons. It also just so happens to have 6 neutrons. Okay, 6 plus 6 is 12. An isotope of carbon is C14. That's what we use for dating. So instead of C12, 12 being 6 protons, 6 neutrons, this is a weirdo. This guy has 8 neutrons. 6 plus 8 is 14. Carbon 14. Okie dokie. I'm going to show you a picture in a minute. It's still carbon, but it's an isotope of carbon because we've changed the number of neutrons, so the mass number just changed. Okay? Please don't worry about atomic weight. And what else was I going to say? Also, whenever something is tiny, it's not test material. But these isotopes are usually unstable, and so they're always trying to decompose into a more stable form. Okay. Some of them, when they do that, they throw off little subatomic particles that you don't need to know about, alpha, beta, gamma radiation, and that causes them to be radioactive. I'm just letting you know that not all isotopes are radioactive, and even if they are radioactive, it doesn't mean that they are a severe danger to anything. Also, because I have this written tiny, atomic weight is not a test question. Okay, so here we go. Hydrogen. On the periodic table, this is how you see hydrogen. And I already showed him to you. He's the weirdo that doesn't have a proton. Regular old hydrogen is also called protium because he's got 1 proton and no neutrons. That's how he gets his name. So this is regular old hydrogen. Deuterium is an isotope of hydrogen. He has a different number of neutrons. Remember, proton has to stay the same. If you change the proton, maybe just write that down somewhere. You change the proton number, you've changed the element. Isotopes are changing the number of neutrons. So here's regular old hydrogen. Here's an isotope of hydrogen. Here's an isotope of hydrogen. Deuterium has 1 neutron. Tritium has 2 neutrons, and even if you don't know about this guy, you know about this guy. He's used in atomic warfare. He can make an atomic bomb. Okay, so I mentioned already that these radioisotopes can be used as tools. And so we can use them, say, for example, carbon dating. Here's another one. You've probably heard of a PET scan. Well, a PET scan uses a radioisotope of glucose, and it highlights inside the body wherever there's a cancer. It's not a bad radioisotope. Now, some radioisotopes can damage living tissue, but sometimes we use it in a good way. Like right here, we're talking about maybe destroying different types of cancer by using a radioactive substance. Now, unfortunately, some of them do cause cancer, but they're not all bad. Okay, molecules and compounds. We're going to take some atoms. Atoms don't like to be alone. They like to bond with something, whether it's another one of themselves or something else. But they will bond together to form a molecule or a compound. A molecule is small and a compound is bigger, and that's really all you need to know. Okay. Sometimes you can put matter together and it mixes together without bonding, without creating a chemical bond. Okay? So, in biology, a lot of the time we're going to use the term water is the universal solvent. The solvent is when we have a mixture, so we're putting some different molecules together, putting different matter together. The solvent is the part of the mixture that's the majority of it. The solute is what you put in there that's in smaller amounts, okay? In biology, the only solvent that we're going to deal with is water. If you work as an auto mechanic or you've worked, whatever in a garage, or shoot, if you love organic chemistry, you've met lots of other kind of solvents, and you've worn gloves and you've worn masks because some solvents are kind of dangerous. We're not doing that. We're in biology. Our solvent is going to be water. In our body, we have mostly water, and we're going to dissolve things in it. Okay. Your blood is a large portion water with some cells floating around in it and some proteins floating around in it. How about that? Okay. So these mixtures, they're not chemically bound together. Mixtures can be solid, liquid, or gas, and they can usually be separated. They separated physically. Maybe you have some salt water, and maybe you have a saltwater pool. How about that one? And you've been splashing around, and it got on the chair, and now it's August, and it's 105 degrees, and the water evaporates. What's left behind? The salt that was mixed in it. The water wasn't bound to a salt. It was just they were living together. Blood. If you work in a hospital, you have pulled somebody's blood maybe, and you spin it down. The cells go to the bottom, the serum goes to the top, because it was a mixture. It was a suspension. And so you can physically separate them. You get the idea. So if I say salt water, you have a saltwater pool. Water is the solvent. Salt is the solute. It's what you put in it. Okay. Okay, on the previous slide, I can't remember if I said this, but there's 3 kinds of mixtures that we're going to talk about. We're going to have solutions and colloids and suspensions. So a solution is a homogeneous mixture, which means that everything is distributed equally. If I have some salt water and I take a little sample from the very top of my beaker, it's going to be the same salt concentration as it is at the bottom of the beaker. So I'm going to test the salt concentration. You take your salt water to Leslie's to go see if your salt concentration is good in your pool. It doesn't matter if they suck that little, you bring in the sample, they suck it from the top, they suck it from the bottom, the answer is going to be the same. That's how much salt is in your pool. Okay. Solutions are usually transparent because they have tiny solutes in them. What else do I want to say? Meh, nothing. Okay, colloid, unlike a suspension on the previous slide, a colloid is not a homogeneous mixture, it's a heterogeneous mixture. So the particles aren't evenly distributed. Those particles, the solutes inside that, that solvent, they're usually a little bit larger. They don't settle out, but it's because they're larger, they're going to make the that mixture look more cloudy. Milk is an example. Sometimes colloids can become different textures. Jello is an excellent example of a colloid. So you mix that gelatin and the coloring and the sugar all together in some water. It's liquid at first, but it can transform, if you change the temperature, into a gel. The colloid that we talk the most about in A&P is cytosol. That is the stuff that all the little organs, the organelles, are floating in. We'll get into that in a little while. We have other colloids too that we touch on in A&P too. Okay, a suspension is also not homogeneous, it's heterogeneous. We have in these, those solutes are visible and they can settle out. That blood that I was talking about that you draw from a patient, you don't have to centrifuge it to get the serum separated from the cells. If you just let it sit there for a little bit, the cells will sink to the bottom and the serum will be on the top. Another example of a suspension that has nothing to do with biology, but it has to do with my one of my things that I used to make for my kids, chocolate chip pancakes. You make pancake mix, and then you put some chocolate chips in it. And then the kids start fighting, so you have to go break it up, and you come back, and all the chocolate chips are back down to the bottom. So then you have to stir it again. And then they start fighting again, and then you know how it goes. But anyway, somebody's going to get more chocolate chips than somebody else because you get tired of stirring. Okay, chemical bonds are relationships between electrons. Electrons in those atoms are what's going to form a molecule or going to form a compound. So the protons aren't the guys that's creating the bond. The neutrons aren't the guys that are creating the bond. It's the electrons that are creating the bond. Here's the shell thing. So I told you that the first shell can hold 2. There we go. And then the next shells, for the purposes of this class, they all want 8. Well, what if we only have 7? 7 is easy peasy setup because we only need 1 electron to finish that shell. But how are we going to do that? We're going to do that by some kind of bond. Okay? Here's a memorization term, the valence shell. Whenever you have a molecule, an atom, the outermost electron shell is called the valence shell. So that lithium earlier that had 2 shells, the first one had 2, the second one only had 1. That's not 8. Anyway, that outer shell with the 1 is the valence shell. That valence shell is the guy where those electrons are going to be the ones that are doing the chemical bonding. The name of the octet rule, the name of that desire to have 8 electrons is called the octet rule. The outer shell, the valence shell, wants 8. And if it doesn't have 8, that is the way a chemical reaction happens. It is the driving force, because if I don't have 8, that atom, once he leaves that periodic table, comes off that piece of paper, he's not happy anymore. He's not balanced. So he's going to want to bind with somebody to make his shell have 8. Most atoms don't have a full valence shell. That's why we have a lot of chemical reactions in the world, which is good, right? Okay, this guy right here, helium, it's not written out, but he has 2 protons and 2 neutrons. It's not drawn. That's okay. This is the nucleus. He has 2 electrons in that first shell. It's the last shell, too, because since he has 2 electrons, it's full. This guy is happy. He is completely happy being all by himself. Neon. Neon is going to have 10 electrons. So here's, this shell is full, 2. The next shells hold 8. 1, 2, 3, 4, 5, 6, 7, 8. So he is completely full too. He is a stable element as well. Helium gas is just helium. He doesn't need to bond with anybody. Neon gas is just neon. Incidentally, if we were in class, I'd show you how they're all the way on the right-hand side of the periodic table. They're called noble gases. They're perfectly happy all by themselves. But that's not the way it usually is. So hydrogen, I've already showed you. There's 1 proton, so there's 1 electron. How many does this shell want? He wants 2. That's the first shell. Because it's the only shell, that's the valence shell. So he's very reactive. Hydrogen reacts with lots of things. Carbon has 6. 6 protons, 6 neutrons, and 6 electrons. Don't memorize that, I'm telling you. It has 6 protons, 6 neutrons, 6 electrons. If I tell you that, though, can you fill up the shells? Okay, if we have a total of 6, 6 minus 2, fill up this shell, move on. 6 minus 2 is 4. 1, 2, 3, 4. Is that shell full? No. He wants 8. Oxygen, let's come down here. 8 protons, 8 neutrons. So he has, if he has 8 protons, 8 makes him oxygen. 8 protons makes him oxygen. Protons makes the element. If he has 8 protons, he has 8 electrons. So 8 minus 2 is 6, so there's 6 left. 6, is that a full shell? No. 8 is a full shell. This guy wants 2 more. You get the idea. So sodium is Na for natrium, but anyway, he has 11 electrons. So 11 minus 2 is 9, minus 8 is 1. 9 minus 8 is 1. So there it is. That valence shell only has 1 electron. So I'm going to ask you a question here on this sodium. Would it be easier to lose that 1 electron, or would it be easier to gain 7 electrons? So the 3 kinds of bonds that we have are ionic bonds, covalent bonds, and hydrogen bonds. And I'm going to go through those today. Ions are atoms that are going to lose or gain an electron and become charged. We do not change the number of protons. And now we don't have equal proton to electron. Remember I said that's all fine and dandy on the periodic table. They're going to be balanced. But in real life, that's not how we're going to go. So what will happen with my question, like that sodium just a minute ago, sodium has 1 in that outer shell. Is it easier to get rid of 1? Or is it easier to gain 7? The answer is it's easier to get rid of 1. If I get rid of that one electron and give it to somebody that needs it, my last shell has 8, right? Because the sodium had 11 electrons. 11 minus 2 is 9. 9 minus 8 is 1. I'm going to give that electron to somebody else. Here you go. If you lose a negative, you become positive. And that's why you usually see sodium written as Na+. Before I forget, calcium is often written as Ca2+. So that tells you right there, calcium has lost 2 electrons. Think of it this way. If you lose a negative person in your life, do you not become more positive? Life's looking up, right? Get rid of that negative Nelly, and then you can be a positive Polly, whatever. I don't know. Anyway, now, if you had 7 electrons in that outside shell, would it be easier to gain an electron or lose 7 electrons? I'll say it again. If on that periodic table you end up with 7 electrons in your valence shell, is it easier to get rid of 7 or is it easier to gain 1? It's easier to gain 1. So chloride is an excellent example. On that periodic table, chloride has 7 electrons in its outer shell. So it's easier to gain 1 electron. An electron is negatively charged. So you often see chloride written as Cl negative because he gained 1 electron. And why don't we write 1 negative? Well, you might remember from algebra in math, we don't write 1x, we just write x. Now, if it's 2x or 3x or 4x, you have to write that. But if it's just x, there's an assumed 1 in front of it. So Cl negative is saying Cl 1 negative electron extra. And that's called an anion. And finally, the last thing I'm going to say on this slide to help you remember the difference between a cation and an anion. Cats are positive creatures. I love dogs and cats, but I know a lot of people just like dogs. If you don't like cats, you just haven't met a good one, because cats can be hilarious. So a cation is a positively charged ion. Ion is the general term for an atom that has a charge. Ion is a general term for an atom that has a charge. Anion is more specific. I have a charge and it's negative. Cation is more specific. I have a charge and I'm positive. So an anion is an ion with a negative charge. A cation is an ion with a positive charge. So what happens then if sodium, here we go, this is a fantastic picture. This is showing how he is on the periodic table with his 1 on the outside. And then here's chloride with how he is from the periodic table with 7 on the outside. Sodium says, here you go, I see that you desperately need that. So now sodium's balanced, now chloride's balanced. Their valence shell each have 8, but he lost an electron, so he's positively charged. He gained an electron, so he's negatively charged. So guess what? They're attracted to each other like magnets. This magnetism is an ionic bond. This magnetism is an ionic bond. These guys are dating. So this is what it looks like. They're magnetically attracted to each other, and they're forming, in this case, a salt. Ionic bonds, listen, ionic bonds are salts acids, and bases. Not organic. This is inorganic. Salts, acids, and bases. Now, salt water. I can add water to this. The water's not going to bind to the salt. It's not going to bind to the sodium. It's not going to bind to the chloride. It's going to surround each of those atoms and separate them out. But not a bond. Salt water is just a solution, a mixture. Now, covalent bonds, what's going to happen is instead of being attracted to each other, like salts, acids, and bases with inorganics, covalent bonds, they're going to start sharing electrons. This is the part that usually gets people confused. So just listen. Covalent bonds share electrons. Covalent bonds are usually organic. And I should say almost everything in anatomy and physiology, it's all science. So the answer is always usually. It's rare that we can use always. Okay. Covalent bonds can be polar or nonpolar. I'm going to show you an example of a covalent bond. We're going to share electrons. Okay, covalent sharing, not an attraction. We're sharing. We're getting married. Ionic dating. Covalence marriage. Okay. So I told you earlier, carbon has 6 protons, so therefore it has 6 neutrons. 6 electrons. He does have 6 neutrons. Who cares? Okay. So 6 electrons. 1, 2, I filled that shell. 6 minus 2 is 4. There's 4 left. He still wants 4 more. Hydrogen is so easy to bond with because look how he is. Hydrogen has 1 proton, so 1 electron. He needs to fill that shell. He needs 1 more. So look what's going to happen. I'm going to marry you. Your electron is mine, and my electron is yours. Here. Your electron is mine, and my electron is yours. This is completing this. Now, 1 hydrogen wouldn't be enough, right? You have to have 4 because he has 1, 2, 3, 4 electrons. So the carbon needs 4 hydrogens to finish it out. This is actually the most common molecule on Earth, methane. So he's happy, he's got 2. 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 2, 4, 6, 8. Ta-da! Do you understand that concept? He needs 8. They're married. They're sharing. This isn't just an attraction. This is not dating. This is not based on charge. This is all about sharing. Can you remember that? This is what organic molecules usually do. So, on that previous one, they each shared 1 electron. So, the carbon shared 1 of hydrogen's electrons. Hydrogen shared 1 electron. That was a single bond. Okay, oxygen has 6 electrons. 1, 2, 3, 4, 5, 6. So he needs 2 more. 1, 2. They got married in 2 spots. This is a double bond. 1, 2. It's usually written like this. If it was a single line, it would be a single bond. If it was 3 lines, it'd be a triple bond. As in, boom, nitrogen. So nitrogen, on the outside of his valence shell, he has 5 electrons. So, in this case, they each need 3. And so, 1, 2, 3. They got married in 3 different spots. 1, 2, 3. Notice how these guys are lining up in a line. They're sharing equally. Whenever they share equally, it's called a non-polar bond. And then what happens is the electricity is equally balanced. And memorize this, non-polar bonds are hydrophobic. They do not like water. So they're sharing equally. It's going to make a lot more sense when I show you a polar bond. But nitrogen needed 3, nitrogen needed 3, of course. We're sharing equally. We're in a straight line. If I showed you CO2, it also would be in a straight line. This is one of those weird exceptions where carbon dioxide, C2 oxygens dioxide. This is one of those weird exceptions where carbon is making up an inorganic molecule. Ah, look, perfect. I forgot the slide was on here. So this is the carbon in the middle. You remember oxygen needed 2? Oxygen needed 2. You remember carbon needed 4? So methane, it had 4 hydrogens. That's a totally different molecule. On this case, oxygen needed 2. So here, let me share 2 of your electrons. This oxygen needed 2. Here, let me share 2 of your electrons. I got 2 electrons on this side, 2 electrons on this side. So the carbon got the 4 that it needs. And look how they line up. That is also a non-polar bond. If it's non-polar, you're going to memorize this. Non-polar is hydrophobic. What does that mean? Hydro, water, phobic, fear of. Oil and water don't mix. Oil is hydrophobic. So these are all examples of non-polar covalent bonds. They're sharing equally. Polar covalent bonds is unequal sharing. And I'm going to show you a picture and hopefully it makes sense. So if I tell you that non-polar is hydrophobic, then you also need to memorize that if it's polar, it's hydrophilic. It loves water. As a matter of fact, one of the most, the most common polar molecules is water. I love myself. Okay. So it's easier for me to show you this than to go through this slide. This little part right here, don't worry about the term dipole. I should unhighlight that. Okay, so this is how water actually sets up house. See how it's kind of at a V right here? It's not linear. So let me explain into a little bit more detail about why it's not linear. Do you remember oxygen had 6 protons? Hydrogen had 1. If he had 6 protons, he had 6 electrons. He needs 2 more. Hydrogen needs 1 more, right? 1 proton, 1 electron. I'm going to share 1 of mine with oxygen. I'm going to share 1 of mine with oxygen. And vice versa. Oxygen share 1 with hydrogen. But oxygen has 6 protons. Hydrogen just has 1. So what's going to happen is those 6 protons are going to pull a lot harder on that electron than hydrogen can. It's like having 6 people on one side of the tug-of-war rope, 6 protons, to 1 person on the other side of the tug-of-war rope, 1 proton. They're bound because they're married. But because oxygen has 6 protons on the tug-of-war rope, the electrons prefer to hang out on this side of the molecule. And hanging out on this side of the molecule makes this molecule not perfectly balanced with its charge. In other words, you have more electrons hanging out on this side of the molecule because the 6 protons are pulling harder. That makes it a lopsided. They're bound. That is a molecule. But if you were to take a, it's drawing a blank, the thing that measures electricity. Electrode? No. Anyway, the thing that measures electricity, you would notice that because the oxygen is tugging harder on the electrons, because there's 6 of the protons, this side of the molecule is going to be more negative than this side of the molecule because the electrons are hanging out closer to here. Because of that weird extra pull, that makes it a lopsided molecule, and it is called polar. So here's a summary. We're going to have, with ionic bonds, we're going to transfer the electrons, and now that atom has a charge. Because they have a charge, they're attracted to each other, they're dating. Covalent bonds, we're sharing electrons. They're married. Whether it's polar or nonpolar, they're married. They're linked together by their electrons. But with nonpolar, it's all equal sharing, and the charge is equally distributed across that molecule, making it linear. Nonpolar, the most important thing to know from this, nonpolar is hydrophobic. Polar is unequal sharing of the electrons, so there's a lopsided charge. One side is more negative, one side is more positive. Now, why is that important? Because I have to introduce another kind of bond that's going to come into play whenever we're talking about this. And that's the hydrogen bond. It's not a very strong bond. The ionic bond and the covalent bond, those are strong bonds. Okay? This is more like a weak magnetic attraction. So that I just showed you that oxygen was partially negative. I forgot to tell you that it's that lambda positive means partially positive, and then the lambda negative on the hydrogens means partially negative. So you know how you have a little drop of water on your table and you put another little drop of water on your table. You can take your fingertip and drag them next to each other, and now those 2 little drops of water are one slightly bigger puddle of water. But you can take your hand and slap that little puddle that you made, and now there's not just 2, there's like a whole bunch of little splatterings of water everywhere, right? That partial negative on the oxygen of water is attracted to the partial positive of the hydrogen on the water. They're attracted to each other. But because it's a weak magnetic attraction, it's easy to break. It's a good thing because on a DNA molecule, those rungs in the middle of the ladder are easily divided so that we can go through mitosis in your DNA.
The atoms that make up a water molecule are in a constant tug-of-war over their shared electrons. Oxygen exerts a far stronger pull on the shared electrons than does hydrogen, and so the electrons spend more of their time closer to the oxygen atom. Because of this unequal sharing of electrons, the oxygen atom in a water molecule actually has a slight negative charge, and each hydrogen atom has a slight positive charge, even though the water molecule as a whole is neutral. Because of the unequal sharing of electrons and the resulting positive and negative poles, a water molecule is said to be polar. The polarity of water molecules causes them to be attracted to each other. Since the positively charged atom involved in this special type of attraction is always a hydrogen atom, this kind of bond between molecules is called a hydrogen bond. Each water molecule can hydrogen bond to 4 other water molecules. A hydrogen bond is weak and lasts only a tiny fraction of a second, but it takes a lot of energy to overcome the combined attraction of many hydrogen bonds. This explains water's great capacity to store heat, its high boiling point, surface tension, and several other unusual properties.
So here's a picture of what I just said. The oxygen is partially negative because you have 6 protons here tugging on the electrons. He just has 1 proton tugging on the electron. So the electrons are hanging out closer to the oxygen. So the electrons are creating a partial negative charge here on the oxygen. And because they're further away from the hydrogen, this side of the molecule is partially positive. But here's another water molecule. Negative is attracted to positive, so we get a little hydrogen bond. For these kind of bonds, we just draw a little dotted line instead of a dash because it's so weak. This hydrogen bonding creates the surface tension on water that allows things like a spider or this water strider to walk on the surface of the water. All right, enough about bonds. Chemical reactions. So chemical reactions is what's going to happen when we take that chemical bond, we break it, we bind to something else. Maybe we just rearrange all the molecules. Chemical reactions are written in equations, and one side of an equation is going to be the reactants, and the other side is going to be the product. Nah. Okay, so here is this right here is one equation. Okay, a hydrogen plus a hydrogen yields H2, hydrogen gas. 4 hydrogens plus 1 carbon yields CH4, which is methane gas. This side is the reactant. The arrow points to what the product is. What happens? We're going to have a reaction right here. What is the final product? So the arrow is what yields the product. This side would be the reactant, this side would be the product. If that arrow was pointing the other way, then this would be the reactants and this would be the products. So the arrow is pointing to the product. So if we're going to make something, if we're going to build something, remember that's anabolic. The steroids, anabolic steroids, that guy built up some ridiculous muscles, did he not? Anabolic is building or synthesizing. So a synthesis reaction is about building up something. A plus B, they get together. We've got AB. There is an unseen bond in here. There's nothing drawn, but they are bound. So amino acids coming together make a protein. Vice versa. If we were doing a catabolic reaction, the arrow would go in this way. If we were breaking up this protein, breaking them up into amino acids. That would be a catabolic reaction, which is also called decomposition. If we're going to decompose something, we're breaking it up. So we have broken a bond here and created A plus B. They've been separated. Broke something up, so we probably lost a little bit of heat. In your liver, you ate 12 Snickers bars before you came to class. You didn't need that much sugar. So your body's going to use the glucose that you need, and it's going to store the rest in your liver as glycogen. So let's say you've been studying for your anatomy test for 12 hours and you haven't eaten. Your liver is going to break down or decompose that glycogen so you can have the glucose that you need, because your cells need glucose, even though you're not putting anything in your mouth. That's a decomposition reaction. Catabolism. And then an exchange is simply that. An exchange reaction is AB plus C. We're going to break this bond and recreate a bond right here. B's off by itself. You get the idea. Here's another example. Synthesis. I'm going to make something. Note is different from book. They're different. I'm going to combine them to make something totally different. A notebook. I have synthesized something. The energy that is, so when I put things together, energy is stored inside this bond. Whenever you see a bond, think energy. There's energy in a bond. When you break a bond, you've released energy. So when you build something, you store energy. When you break up something, you release energy. Here's something. Bookworm being decomposed into a book and a worm. They're different, right? A bookworm is not a book. Bookworm is not a worm. I've broken them up and I've released energy. And I have two different products. Reactant, product, reactant, product. And finally, exchange reaction, notebook plus worm. I'm going to break a bond here, but I'm actually going to form a bond over here. So I've exchanged the energy. I broke a bond, so I release some energy, but then I use that energy and stored it in this bond right here. It's in there. So whenever you bind things, you store energy. Whenever you break up something, you release energy. You synthesize here something, you decompose something right here, and this you just exchange something. Skip that, although I think the reason I left this in here, this is a phenomenal chemical reaction, chemical equation to take note. C6H12O6 is glucose plus oxygen yields carbon dioxide, water, and energy. Sugar plus oxygen yields carbon dioxide, water, and energy. That's what happens inside your little mitochondria. Maybe you've heard of that guy. Okay. Whenever we release, this is a memorization. Whenever you release energy, whenever you break a bond, that's an exergonic reaction. So a decomposition reaction, when you break something up, is an exergonic reaction. An endergonic reaction is when you build up something and you store energy inside of a bond. So that would be a synthesis reaction. In theory, all chemical reactions are reversible, but in the human body, as far as biology goes, it usually requires too much energy to go backwards. So in chemistry, yes, they're reversible, but for the purposes of this class, in anatomy and physiology, we don't usually reverse things. It's going to go a different route. Okay, this is going to be in lab. The rate of chemical reactions can be manipulated. If you change the temperature of your body, you can change the rate of chemical reactions. If you change the concentration of the reactants, you can change the rate of the reactions. Different particles behave differently, and so therefore can change the rate of reaction. A catalyst. In the human body, the catalyst is an enzyme. Enzymes change the rate of a reaction. And then finally, what are we dealing with? What kind of element are we dealing with? I already told you that helium is a noble gas. He's perfectly happy all by himself. He's not reacting with anybody. But sodium, who's got that one electron sitting on the outside of him, or hydrogen, they're very reactive. So depending on what the reactants are determines also how fast is that chemical reaction. So a catalyst, we have different kind of catalysts in chemistry, but we're in biology class, so the catalyst that we're going to talk about is enzymes. Will something break down without an enzyme? Yes, but not very well. If you are lactose intolerant, you know exactly what I'm talking about. Lactase, lacking lactase makes it very hard for you to break down milk. Are you going to poop out milk? No. Something's going to happen to that milk, but you're going to get a bellyache in the middle of it all because it's so very hard for you. Little video about hydrogen bonds. Highly recommend watching that. Might do that.